There. So in this exercise, we got set V, that in this case is going to be R, the real numbers, equipped with the usual summation and multiplication of numbers. And we need to check that this corresponds to a vector space. And this is a quite trivial exercise because we know how the axioms on the reals work. And in this case, the scalars that we're defined on this vector space are again real numbers, so they're the same. And we know that the distributive property is holds on the real, so it is really easy to check that all the axioms of a vector space are satisfied. So let's start. So the first thing that we need to check, the first axiom that we're going to prove, is the one that state that the summation should be closed. That means if I pick A and V real numbers, then the summation of these two elements is also a real number. We know that the sum of two real numbers is again a real number, so this is true. This is, well, please don't confuse. Here should be with the vector space V, but in this case the vector space is R, it's just the real number, so that's why this is trivial. The second axiom say that given two vectors A and V, in this case is a real number, then the summation commutes. And we know that this is true for all the real numbers, so checked. Then we need to check the associativity. So again, given A, V, and C on the vector space, in this case is R, we need to check that A plus B plus C is equals to A plus B plus C. But we know that the associativity holds on the real, so this is also true, is checked. Then the fourth axiom say the existence of the neutral element. That means that there exists a neutral element on the vector space, but in this case is vector space are just the real numbers, and this neutral element corresponds to the zero number. And why the zero? Well, because it satisfies the axiom that A plus zero is equals to 0 plus A, and this is just A again. So this is true for all the real numbers, so checked. The axiom number 5, it says that for all the elements on the vector space, in this case the real numbers, which is a real number, then there exists a unique inverse that is written as minus A, such that A plus minus A is equals to the neutral element, in this case 0. And we know that the negative numbers are also part of the real numbers. So if we take some element A and then we change the sign, then when we sum together these two elements, that's going to be equals to 0. So that's true for all the real numbers, so checked. Then we need to consider the actions related to the scalar multiplication, but here is quite trivial because k and m are also real numbers, and the vectors in this case a, b, and c are also real numbers. So let's see what happened here. So the axiom number 6, say that if I take a vector, and then I multiply by a scalar, in this case k times a, this should be also be part of the vector space, in this case R. Keep that in mind. And this is true because this is just a multiplication of real numbers. The multiplication of two real numbers is again a real number, so this is true. The seventh axiom says that the distributivity property k a plus b. Here a and b are vectors, but they are the real numbers. So this should be equals to ka plus kb. And this is true because all these elements are real numbers, so the real numbers have the distributivity property, so this holds. The axiom number 8 is the same, but now considering two scalars, but in this case scalars and vectors are the same thing, so here again it holds kb plus mb. Why? Because all these elements are real numbers, so it is actually the same to the previous case, so it holds. Number 9, say the multiplication and distribute the associativity on the multiplication in this current multiplication. Okay, a, again here all the elements are real numbers, they're just numbers, so all these are equals to kma, so it holds. And finally, the last axiom of a vector space say that there exists the identity element, that means the 1 in this case. The number 1 is an element of the reals and satisfy that if we take a real number and we multiply by 1, you obtain again the same number. So this is the identity, and it also holds in this space. So the conclusion is that R equipped with the usual summation and multiplication is a vector space.